Oh, okay. My apologies. I will fix that. Okay. Oh, okay. I'm sorry. It apologize about that.
Now,
Now let me see if I can.
okay.
Slideshow.
Okay, hang on.
Slideshow.
Yeah, it did it. It did it on a different. It does it. It's doing it on a different monitor. I apologize. It's showing it on a monitor you can't see. Let me see if I can escape out of here and select a different monitor. Apologize for this difficulty here we're having. And just go, yeah.
Keith, on the team, you select the other monitor, it should be fine, right?
Yeah, I'm doing that. It's a little slow. Apologize for that. Okay. Is it it's still not working? Let me hang on, let me back out of here and see if we can figure this out. Okay, I'm gonna have to move on here. I can't get it. It's not.
Would it help if I was to share the presentation, Keith, and I can move the slides for you?
Maybe we can. Yeah, I'm having some troubles here with my monitors. Let me try this one more time. Let me try this. It's not letting me select the monitor that
we can see it now.
You can see it now.
We can, yes. We had it.
Okay. Let me try this one more time. I apologize for this. Can you see it now?
Good.
Yes.
Yes.
Are we good?
We're good.
Okay.
Perfect.
Sorry about that. Let's start over. My name is Keith Bellingham. I'm a soil scientist at Stevens Water Monitoring Systems, and today we are going to talk about landslides and the parameters used for risk assessment. And start off here. So landslides occur quite often across a variety of different landscapes. Landslides pose a major threat to human lives and property and infrastructure. Climate change and urban growth, deforestation, and other land use changes and land use considerations are all factors that can affect landslides. So a risk safety factor for measured parameters can be developed to provide an early warning system. So there can be an analysis of the soil and monitoring that can help identify the risk and help even to predict the risk and assess the risk of landslides. And so that's what we're going to talk about today at a technical level. One of the main agencies in the United States that monitor and assess landslides is the United States Geological Survey, and they published this map that has all of the landslide occurrences over the past several years. And most of these landslide occurrences happen in areas where there's a lot of slope and a lot of rainfall. A real-time monitoring and soil testing can be used to develop a safety risk factor. The parameters influencing the properties of landslides have been identified in the scientific literature and can be included in a calculation for a risk factor. There's a wide variety of predictive models found in the literature. A landslide safety risk factor and a monitoring an algorithm, it's very site specific, and it would need to be developed before using to warn the public. And I'd also like to point out that there's no single formula or no single method for developing a landslide risk factor. It has to be developed scientifically, and it's very site specific. So some of the parameters that are used to that affect landslides. First is the hill slope. The steeper the slope, the more the risk there is. Precipitation is a big factor, and precipitation affects the weight and density of the soil. And we're going to talk more about that here within the next couple of slides. Precipitation is used in lots of the models used in the literature. A lot of the models in the literature use what's called the antecedent rainfall, and the word antecedent means in the past. And in this case, the antecedent rainfall in these models typically are the rainfall over the past 24 hours or the rainfall over the past week, also with the intensity of that rain. So it's a combination of the amount of rain over a period of time and an intensity of rain. And that's called the antecedent rainfall. There's also a forecasted rainfall as well. Vegetation also plays a major role in the assessment of a landslide. Vegetation promotes evapotranspiration, which helps dewater the soil. Evapotranspiration is a combination of evaporation from water out of the soil, and it's also the transpiration of the water out of the soil, basically the root uptake and the evaporation from the plant leaves and the plant itself. That's transpiration. And evapotranspiration is a combination of the two things, which can be measured with meteorological parameters like air temperature and wind speed. Vegetation can also intercept incoming rain. The rain can land on the leaves and subsequently evaporate off of the leaves, and that intercepted water does not make it into the soil. So a bare soil that receives an amount of rain, the soil would get wetter if there's no vegetation, because it would first hit the vegetation and evaporate off the leaves before dripping down and saturating the soil. Second, and the third point with vegetation is the roots. The roots play a major role in holding the soil particles in place. In a number of models, there's vegetation indexes or indices for maybe the fraction of bare soil versus vegetation, and in some cases, the types of vegetation have have different indices as well to characterize how vegetated a slope is. There's two geotechnical parameters that are found in the literature. One is called the soil stress cohesion, and it's measured in kilopascals, and also the soil angle of internal friction. It's measured in degrees, and these two parameters are measured in a geotechnical lab. They have to do with how well a soil holds its shape under a stress. That's the angle of internal friction, and the cohesion, how much the soil is held together as an undisturbed core. And these tests are standardized. There's standard methods for these tests, and these geotechnical tests are often performed and used for geotechnical and civil engineering applications, such as construction of roads and bridges and those kinds of applications. The soil properties, as I mentioned before, the water in the soil adds significant weight to the soil. So a typical soil would have a dry bulk density of let's say 1.5 grams per cubic centimeter. As we see on the left here, the formula for bulk density is mass divided by volume. And so if the soil has a density of 1.5 grams per cubic centimeter, the dry soil is going to weigh 1,500 kilograms per cubic meter. If that dry soil were to saturate, and if the saturation is 45%, it's going to add 450 kilograms of mass to that cubic meter of soil for every cubic meter. So water adds significant weight to the soil. And so the next concept I want to introduce is the saturated hydraulic conductivity. And the saturated hydraulic conductivity is a static property of the soil. It's a property of the geologic material. It doesn't change. Once when you measure it, that's the property of that soil, and it has to do with particle size and the type of soil it is. But the saturated hydraulic conductivity comes from Darcy's law. And Darcy's law right here is the velocity of the water times the hydraulic conductivity times the gradient of the hydraulic head to the distance that's separated. And right here I have a diagram explaining Darcy's law. And so if this was completely saturated, that the hydraulic head or the water level in these two pipes here, separated by this distance, you can use this formula here to calculate the velocity of the water moving through the material. So the saturated hydraulic conductivity is a factor that that's used to determine drainage and how well water moves through soil. On this table here in the bottom, we have the different hydraulic conductivities for different materials. The unit is centimeters per second for saturated hydraulic conductivity, and we see that gravel has a saturated hydraulic conductivity of 10. Sand is 1, but as you can see, as you get more clay rich, as the soil gets more clay, you move 8 orders of magnitude. So a fine textured clay is 8 times 10 to the negative 8th centimeters per second, whereas sand is 1. So 8 orders of magnitude in difference for this parameter, or saturated hydraulic conductivity. Another concept that's very important in soil hydrology is called the field capacity. And I'm going to explain what the field capacity is for many of you that don't know. On the right here, we have the soil textural triangle. On this axis, there's your percent clay. On this axis, you have the percent silt, and on the bottom axis, you have the percent sand. And depending on the percent sand, silt, and clay, where it falls in this triangle gives you the soil texture. And many factors in soil science are determined and correlated to a soil's texture. Field capacity is also correlated heavily with the texture of the soil. As we see in this graph, the blue line is the soil's field capacity. And as we see, as we get more clay rich, the field capacity goes up. Field capacity is the point at which it's the soil moisture when gravity stops pulling water out of soil. So if soil is completely saturated and completely wet, the soil's field capacity is the soil moisture after the soil drains. When gravity, the force of gravity, pulls all the water out, and the only water left in the soil is what's there, what's being held in place by the capillary forces. So it's where capillarity forces equals gravity. And as we can see, the more clay rich the soil is, the higher the field capacity. For example, a sand, the water runs right out, whereas a thick clay, the water stays in for a very long time, and it has a very high field capacity. So above field capacity, the water is draining out by gravity. Below field capacity, the water moves very slow and is held in the soil pores. To illustrate this, we have a graph, and on the x-axis of the graph is time. This is about 1 month of data. And on the y-axis, we have soil moisture. And we see that the green line is field capacity for this type of soil. This is a silt soil that's about 5% organic matter. And we see the rain events occur. As the rain event occurs, we have a sharp increase in soil moisture all the way up to its saturation, which is about 50%. And then when it stops raining, the water soil moisture falls very rapidly indeed, until it hits this point where it slows down. That is where the water transitions from being pulled by gravity to being pulled by capillary forces. And it's the elbow in the dewatering curve. As we can see in this green line, we can see the elbow inflection point on the dewatering is where the field capacity is by determining, this is a good way of determining what the field capacity is by looking at time series soil moisture data. And so in this example here, one factor with landslides, it's the amount of time the soil stays at or above field capacity influences the risk of landslides. In this example here, this is about 1 month of data. This big cluster here of these rain events, the soil is staying at or above field capacity for about 3.2 days. And then maybe a half a day, for these other rain events. This inflection point is determined mathematically by a slope, a rolling slope. When the rolling slope reaches a certain threshold on the dewatering side of the hydrograph, that is equal to field capacity. It's the inflection point of when the water transitions from being pulled by gravity to transitions from gravity pull to capillarity, or otherwise called wicking. So there's two main zones in the subsurface. We have the groundwater, or the saturated zone. This would be the aquifer. And in some cases, there's monitoring wells to monitor the water level in the aquifer. And then this is the aquifer, or below the water table. This is where the soil and the geologic media stays wet all of the time. And it feeds streams and comes out as springs. And this water table can fluctuate oftentimes seasonally. And then above the water table, we have what's called the unsaturated zone. It's also called the vadose zone, and this is where the soil is not saturated all the time. It's where the roots of plants are. It's where roots get their water, and it can vary in soil moisture. It's the part of the subsurface that receives the rainfall, and it's the part of the subsurface that is influenced by evapotranspiration. And again, it's where the plants take the root, take their water up from. And this is where we would plant. This is where we would install the soil moisture sensors. If there's a monitoring well going down to the aquifer, then the aquifer could be monitored with a pressure transducer. The water movement in the groundwater, where in the saturated zone, is primarily characterized by Darcy's law, which we already talked about. And in Darcy's law, the hydraulic conductivity stays relatively constant. In the soil, the water moves primarily by wicking. When it's below its field capacity, the movement of water is much slower, and it's influenced by wicking, and it's influenced by evapotranspiration. Another parameter that we need to define is the hydraulic head of the soil. The hydraulic head is closely related to the matrix potential. They're almost the same thing. The hydraulic head is measured in meters, negative meters, and the matrix potential is measured in hectopascals, or a unit of pressure, oftentimes bar. And what the matrix potential is, it's the amount of pressure it takes to pull water out of soil. So it's the suction. The drier the soil, the more suction it takes to pull the water out of the soil. Here we have a diagram of a hanging water column. So if this is soil samples, and this is and these are saturated, and we were to hang a hose or a water tube full of water, the hydraulic head of the suction is the height of the hose. The height of the hose in meters is equal to its hydraulic head. And if you were to measure the pressure of that of course would be the matrix potential. So they're very closely related. They're just different units. One's measured in meters and the other is measured in units of pressure, like bar or hectopascals. Another unit you might see is called the PF. The PF is the log of the matrix potential. And this is convenient for when pressures get very, very high. They get in the millions, and it's easier to, mathematically, it's easier to use the log of the pressure, because if the pressure gets into the tens of thousands or millions, then taking the log of it is an easier number to deal with. You see that the PF in the scientific literature. So another important aspect to soil hydrology is the soil water retention curve. The soil water retention curve is a plot. It's the soil moisture percentage on the y-axis, and it is the pressure or the matrix potential on the x-axis. And if you plot that out, each type of soil has a different curve. We see sand in red here, and which is a very different curvature than clay, which wants to hang onto soil. And as you increase the pressure, the more water comes out. So for a sand, it just takes a little bit of pressure, a little bit of suction to pull all the water out, to go down from 40% to 5% with just 2 bar of pressure. Whereas with the clay, it takes many hundreds or thousands of bar of pressure just to get a little bit of water out. And so this is your soil water retention curve. We're going to talk a little bit about the soil water retention curve and how this is useful. Now you can use this information and how you can measure a soil water retention curve to assess the soil and assess the the drainage, which in turn helps you assess the risk of landslides. So the Van Houten equation is a mathematical transformation that describes the soil water retention curve. The Van Houten equation is quite common and is used in lots of industries, in agriculture, and all kinds of models involving soil water content. And we'll talk a little bit about this and what these parameters are and how to measure them. But the Van Houten equation is a mathematical description of this curve. So with the Van Houten equation and then with the saturated hydraulic conductivity, we can calculate the unsaturated hydraulic conductivity, which is a function of moisture content. So as the moisture content changes, the unsaturated hydraulic conductivity of soil is going to change. And it's that unsaturated hydraulic conductivity that's changing in the soil, which determines how well the water drains out of the soil. So with this water retention curve, the first parameter here is the soil water residual. This is a drier condition. The next parameter is theta S, which is the soil moisture at saturation. Alpha is the air entry value. N is a fitting parameter, and H is the hydraulic head. And so to look at this a little closer, here we have our soil water retention curve. We have our pressure on the x-axis. We have our soil moisture again on our y-axis. And then right at the top, we have our saturation right here. And then our alpha value is called the air entry value. So right when the slope, right, this first inflection point where the air enters the soil upon adding pressure, that's your air entry value, and that's the alpha in the Van Houten equation. Next is your field capacity. That's the another after the inflection point on the drying curve is your field capacity. That occurs at 1/3 bar of pressure for most soils. And then we have the drying part, and then the soil water residual is the next reflection, the next inflection point. The next slide will show the soil water residual a little better, but the next point on this is the permanent wilting point, which is defined as 15 bar of suction. And permanent wilting point is also an important threshold, hydrological threshold in soil, because that's the point at which a plant can no longer take water out of soil. So at 15 bar, that's fairly dry, and a plant can no longer pull water out of the soil with its roots. And to visually look at that, at what the soil looks like under these various parts of the soil water retention curve, we have saturation, which is where all of the particles are completely saturated. All of the void spaces are completely full of water. Then we have the variable water content, where there's air pockets of water, but all of the water in the soil is interconnected through microscopic channels of water. And then at soil residual is where the pockets of water in the soil, these little microscopic pores, become broken. They become disconnected from one another. And we see this on the soil water retention curve, because it's when the pressure starts increasing, but the soil moisture stops going down dramatically. So it's this inflection point. And so with these parameters, soil saturation, the soil water residual, and the air entry value, you can solve the Van Houten equation, get the soil water retention curve, and then calculate the unsaturated hydraulic conductivity, which can be used to assess how well the soil drains. Next, we want to talk about possible monitoring stations. Here's a cross-section of a landslide. Typically, you would put a monitoring station in a place where the slope is steep and where human lives and property are at risk of a landslide. Typically in the steepest part. You can test the soils. You can look at these geotechnical parameters such as your stress cohesion and your angle of internal friction. Can be used to assess where to put the station. But also you can also use the soil water retention curve of a particular soil and determine a drainage index that can help you compare two different soils and the susceptibility for landslides. So here we have two different soils. We have a sandy loam and we have a clay-rich soil, and they have very different water retention curves. As you can see, with just a little bit of pressure, a lot of water comes out of the sandy soil. However, the clay-rich soil still retains lots of water, and it takes a lot of pressure to get that water out. If we calculate the unsaturated hydraulic conductivity and plot that as a function of soil moisture, here we see the sand soil. These dotted lines are the saturation points for these two soils. So the clay soil is this blue line on the bottom, and as you can see, the unsaturated hydraulic conductivity is almost the same as the saturated hydraulic conductivity all the way. So it's a very poorly conductive soil, whereas the sand, it saturates much lower than the clay, and it has a very nonlinear decrease in unsaturated hydraulic conductivity. And so if you take the integral and take the area under these curves, the bigger the area, the bigger the area, the better the drainage. And so as we see in these two graphs here, the area under the curve of the clay is very small, and the area under the curve of the sand is very, very big, saying that the drainage of the sand is much greater. And this particular mathematical model can be used to compare two different soils, to compare the drainage capabilities. And again, this comes from the soil water retention curve and the saturated hydraulic conductivity. And this can be calculated, and this can be calculated fairly easily once when you have the soil water retention curve. So next, it's possible to arrive at a factor that can be used to be calculated in real time from a monitoring station. First, in a risk factor calculation such as this, again, it's just a risk factor. It's just a probability of risk. It's not going to tell you like what time of day the landslide's going to occur. It's just a risk assessment. The first thing about this equation is that it has weighting coefficients. So it depends on how you can adjust these weighting coefficients to assign how important a particular parameter or a particular component of this equation can be in the overall calculation of the factor. So it's all very site specific, and it would have to be developed scientifically. One parameter that's very important is this first one here called TFC, and this is the time the soil stays at or above field capacity. So this is the wettest, heaviest point that the soil will be after the precipitation events. And this can be calculated with 3 to 4 soil moisture sensors in a profile, and that moisture can be averaged. And then you can calculate when you calculate and know what the field capacity is, you can calculate the amount of time it stays above field capacity. The next factor is the density of the soil, and that's a direct measure of the soil moisture. As we saw from the previous calculation, the weight of the soil increases dramatically with the amount of water content. And so this parameter here could be, you could take the dry density of the soil and subtract it from the wet density to get a difference in density. And that difference in density, of course, you need the dry bulk density of the soil, but also the soil monitoring can help you get that factor. The other two factors are the precipitation minus the ET in the past, over the past days or weeks. And then the final factor is the future or predicted precipitation and ET for what's like the forecast of what's to come. That can also be included in the risk factor. So some of the tools that we have to calculate these parameters, right here we have, these are extraction vessels. These are pressurized vessels that soil samples can be put in to construct a soil water retention curve. They can go from 0 to 15 bar. They can hold lots of soil samples. These brass rings have a known volume, and they can be weighed to get a volumetric water content. And the pressure can be applied to these chambers. It can blow the water out the bottom, and you can condition the soil to be a certain matrix potential, and then calculate the volumetric water content, and then start creating points for the soil water retention curve for that particular soil. The next device here is a TempiCell. This can be used to calculate the porosity of the soil, and the porosity is equal to the soil moisture at saturation, which was one of the key parameters in the Van Huntington equation. You can also calculate the dry bulk density of soil in the same experiment with the brass rings. And then finally, we have permeometers, and a permeometer measures the saturated hydraulic conductivity of a soil sample. It can do it two different ways. It can do it using a falling head method or a steady state constant head method, both of which can be used with this setup here on soil samples. There's electronic pressure transducers inside to measure the rate of falling water. So Darcy's law can be used to, and this equipment together can be used to calculate and measure the saturated hydraulic conductivity, which in turn can be used to calculate the unsaturated hydraulic conductivity with the water retention curve you get. And then this analysis will help you make an apples to apples comparison of the drainage properties of the soil. The next is the real-time monitoring in the field. For that, we recommend the Stevens Hydroprobe soil sensor, which can be installed in the soil at various depths. It can measure the volumetric water content very accurately and at multiple depths. This can be connected to a data logger. For that, we recommend the Stevens Steelhead data logger, which can accommodate up to 30 of SDI-12 sensors, including 30 hydroprobes with one logger. This logger can be equipped with a cellular telemetry, and the data can go to a web platform called Skyview 360, where the data can be analyzed, viewed, shared, and managed. Another sensor that can be placed in the soil is called a soil extensiometer. And so these are two metal discs. This rod can be 3 to 15 meters apart. on the slope. And so when moving soil either pushes on or separates these two discs, a signal can be sent to the logger and measure the distance. So this is another warning sensor that can be used and integrated into the warning system. Some other sensors would include weather sensors for measuring evapotranspiration, such as wind speed, wind direction, relative humidity, and solar radiation. We have a variety of rain gauges. These two can also be connected to the steelhead data logger. And then in places where monitoring wells are installed, we can use a submersible pressure transducer to get the water level of the aquifer. And this device here is called the Smart PT, and it is compatible with, again, the steelhead data logger. So in conclusion, site-specific parameters such as vegetation, the slope angle can be used to determine the best place for a monitoring station and determine the risk. Real-time monitoring parameters would include soil moisture, groundwater level, and meteorological parameters for the measurement of rain and evapotranspiration, and as well as the slope movement sensor from the extensiometer. The laboratory parameters would include the geotechnical parameters such as the soil cohesion and the internal friction angle, and of course the saturated hydraulic conductivity along with the soil water retention curve. All of this can be help calculate and develop a risk factor that can be viewed and monitored and managed in the Skyview 360 web platform provided by Stevens Water Monitoring Systems. And then finally, here are some scientific references and some future reading. If you follow the link up here, you should have access to all of the PDFs from all of these publications. And then with that, I would like to thank everybody for attending this evening.
Okay. Thank you for presentation. Okay. Dạ, mấy anh chị mình có câu hỏi nào đặt ra cho anh khi mình có thể bật mic lên để trao đổi trực tiếp, hoặc là nếu các anh chị mà không mở mic được thì có thể nhắn em để em kiểm tra lại mic cho mọi người. Hoặc là mình cũng có thể nhặt câu hỏi trong phần chat thì tụi em sẽ phiên dịch lại toàn tiếng Anh cho anh khi. Mình có cái câu hỏi nào mình đặt ra về các vấn đề sạt lở đất, các công thức tính hay là mấy cái thông số về đánh giá về chỉ tiêu sạt lở thì mình có thể nhắn cho ảnh để anh giải đáp trực tiếp cho bên mình nhé. Trong lúc mà mọi người đang đặt ra câu hỏi hay suy nghĩ câu hỏi thì em cũng xin phép được giới thiệu sơ qua về công ty Trung Hải của bên em. Thì công ty Trung Hải thì được thành lập từ năm 2007 cho tới nay thì cũng đã được hơn 17 năm kinh nghiệm. Và tụi em thì cung cấp các giải pháp là từ nông trại cho tới bàn ăn. Thì nó sẽ bao gồm toàn bộ giải pháp luôn. Thì bao gồm những cái giải pháp như là kiểm tra tình trạng sức khỏe cây trồng hoặc là kiểm tra bệnh cho cây trồng. Ngoài ra thì cũng sẽ có các trạm thời tiết là một số cái thiết bị dùng để kiểm tra đất, kiểu như là như mấy anh chị thấy anh có giới thiệu một số cái dụng cụ thiết bị mà dùng để phân tích mấy cái thông số sạt lở, như là mấy cái bộ CASAT hay là bộ phân tích đường cong thủy lực. Thì ngoài các giải pháp mà của hãng Soil Moisture là bằng phương pháp truyền thống ra, thì tụi em cũng sẽ có thêm một số hãng mới sau này, nó sẽ là những cái thiết bị tự động. Thì những cái thiết bị tự động này thì tụi em sẽ có những cái thông tin riêng và tụi em sẽ gửi riêng cho các anh chị sau buổi hội thảo. Còn nếu như mà mình có quan tâm thêm về một số cái giải pháp về nông nghiệp kiểm tra môi trường như là đất, nước, không khí, hay là một số cái giải pháp kiểm tra sau thu hoạch như là kiểm vi sinh hoặc là kiểm cái lượng chất cấm sau thu hoạch, thì các anh chị có thể liên hệ em qua cái email mà tụi em đã gửi cho các anh chị khi mà mời tham dự hội thảo, hoặc là xác nhận về link cuộc họp này. À, thì cái bên mình có nhiều thiết bị quan trắc như thế, hoặc diện tích cần quan trắc rất rộng. Bên mình dự tính dùng các thông số từ vệ tinh để dự đoán độ dốc, lượng mưa, độ che phủ và thảo trực phục. Có phân tích tính hay tiêu chí. Dạ rồi, em xin cảm ơn câu hỏi của anh Thiện. Ok. Rồi, xong trong lúc mà em chuyển câu hỏi này thì sang tiếng Anh cho anh chuyên gia, anh chị nào mà có câu hỏi nào khác thì cứ đặt ra giúp em nha. Thì cái webinar này thì em tổ chức là tầm khoảng từ 10 giờ tới 10 rưỡi, thì sau đó thì em vẫn sẽ mở cái khung chat này cho mọi người, nên các anh chị nào muốn đặt thêm câu hỏi thì có thể tiếp tục nhắn vào trong khung chat này, hoặc là mình có thể gửi sang email cho bên em, thì tụi em sẽ gửi email qua về cho hãng để nhờ hãng hỗ trợ các câu hỏi tính chuyên môn cao. Hello, Keith.
Hello.
Yes, we have one question.
Okay.
Keith, the question is in the chat.
Okay.
Yeah. We are having two questions from the customer. Yes.
Okay. Okay. So the question is we plan on, we don't have many monitoring devices, because the area is very large. We plan on using satellite parameters to predict slope, rainfall, vegetation cover. Is there a formula or calculation or criteria we can explain more about the calculation? And the answer to that question is it's very site specific. It would need to be developed. Rainfall and soil moisture and the extensiometers are the parameters that can be logged in the field in real time. And the other static parameters like slope and vegetation, those are all characteristics of the site, whereas the loggable parameters would include the soil moisture and the precipitation and the extensiometers. And again, the formula that would take all of this into account, that would have to be developed, and it would have to be weighted appropriately. For example, there's some soils that never reach field capacity, but yet they could still be there still could be a risk for landslides. And so if it ever does reach field capacity, then that weighted factor in the formula would be maybe bigger, or smaller for other parameters that would make less of a difference. So all that would need to be developed. There is no single formula or calculation.
And there's one more question on top, Keith.
He's So the question is, can you explain more about the weighting coefficients? And the weighting coefficients, again, it would be it's the weighting coefficients are numbers that would need to be developed, and it's order of importance. So if in this formula, that an example, if the field capacity of a particular soil is never reached, maybe the drainage is sufficient enough, or maybe even there's overland flow to the point where the field capacity on average is never reached, then maybe this weighting coefficient is maybe less because it's not important because it never gets there. These development of these weighting coefficients, I think a good starting point would be to assign all of them to equal to 1 at first, because you don't know which one would be more important than another. It's an order of importance. And if they're all equally important, then they would all be equal to 1, these weighting coefficients.
Sao biết là các anh chị mình còn câu hỏi nào khác đặt cho anh chuyên gia không ạ? Về các câu hỏi về công thức tính và các phương trình tính toán trong các yếu tố sạt lở đất này á, thì em thấy nó cũng khá là chi tiết, và nó cũng như ảnh tư vấn á, thì cũng không có cái công thức nào nó sẽ cụ thể, do nó cũng sẽ tùy thuộc vào trong các chỉ số rồi các đặc tính tính chất đất tại hiện trường của mình nữa. Nên em nghĩ là trong cái trường hợp này á, khi mà mình làm mà áp dụng cái công thức tính thực tế á, thì tụi em mình có thể liên hệ trực tiếp với anh chuyên gia, hoặc là có thể liên hệ với bên em, thì tụi em có thể sẽ kết nối với ảnh để hỗ trợ mình trong việc mà set up cái công thức tính cái chỉ số sạt lở này. Thì sau cái buổi hội thảo thì tụi em sẽ gửi lại tài liệu và thông tin liên hệ. Thì các anh chị mà mình cần có tụi em hỗ trợ gì thêm thì cứ liên hệ trực tiếp với lại bên em, thì tụi em sẽ kết nối và hỗ trợ thêm cho mình. Hello, Keith. Yeah, we have other question. Yes.
Okay. Yeah, that's a good question. There's lots of machine learning regressions now, and can we, certainly, I haven't really seen any machine learning algorithms used yet in this. I think the reason why is when a landslide occurs, chances are there's probably not a monitoring station and the soil hasn't been analyzed, and there's not a lot of reference data to go on. When I've done machine learning regressions, about 10 points of training data, typically are needed, and that for landslides and the data that's associated with when a landslide occurs might not be available. But I think if you had enough landslides, or maybe you could simulate this in a lab, you could properly use machine learning regressors to assign those weighting coefficients and to help arrive at an equation that could do that. There's lots of tools available. A lot of the machine learning tools now are free. So I think so. Yeah, there would be a way to do that. One of the going back to one of the the questions here, and a lot of the things that are in the current studies in the scientific literature, is mathematically modeling the soil moisture from the meteorological conditions. One such software is called Hydrus, to where if you put the precipitation, the forecast into the model, and as well as the soil water retention curve, you can predict what the soil moisture is going to be from a future rain event. And therefore, you can model and predict into the future the amount of time the soil stays above field capacity. So that can be predicted. And machine learning regressors are also used in that particular model. So I would encourage you to look at Hydrus 1D. There's some references to that model in the reference section of this presentation.
Ok. Biết là các anh chị mình còn câu hỏi hay vấn đề nào mình cần đặt ra cho anh chuyên gia từ hãng không ạ? Dạ rồi. Ờ, mình có còn vấn đề hay có câu hỏi nào thì mình cứ gửi lên cho tụi em, tụi em sẽ hỗ trợ mình dịch, hoặc là ờ, tụi em có thể gửi lại cho bên hãng, thì nhờ anh chuyên gia để hỗ trợ bên mình trả lời các vấn đề. Hoặc là mình có cần hỗ trợ nào trong cái việc mà kiểm tra các công thức tính hay là mấy cái yếu tố sạt lở này kia, thì cũng có thể gửi cho anh. Nếu như mà các anh chị mình chưa suy nghĩ ra câu hỏi hay là mình cũng chưa biết phải hỏi gì á, thì chắc là em cũng xin kết thúc cái buổi webinar ngày hôm nay. Thì mình có cần tụi em hỗ trợ gì thêm thì cứ việc nhắn trực tiếp qua tụi em qua email, hoặc là mình cứ tiếp tục nhắn ở trong cái khung chat này, thì tụi em sẽ mở cho tới hết ngày hôm nay để có thể các anh chị gửi các thông tin cần thiết vào. Thì nay chắc bây giờ cũng hơi trễ so với lại bên 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 Mỹ rồi. Giờ thì bên đó chắc cũng cũng khoảng 8-9 giờ rồi, nên nó cũng xin phép là để cho ảnh anh chuyên gia này ảnh nghỉ ngơi. Thì có cần tụi em hỗ trợ gì thêm thì cứ việc liên hệ trực tiếp với bên em ha, thì tụi em sẽ hỗ trợ hết mình cho các anh chị. Ngoài ra thì sau buổi hội thảo thì tụi em sẽ gửi thêm các tài liệu thông tin về sản phẩm và các cái bản ghi lại cũng như là tài liệu của buổi hội thảo này, và các dạ, em sẽ gửi qua email cả bản ghi và cả cái tài liệu này luôn. Rồi các anh chị mình muốn có đặt thêm câu hỏi hay là có vấn đề gì thì cứ liên hệ trực tiếp với bên em, rồi tụi em sẽ kết nối với lại anh chuyên gia của hãng để hỗ trợ cho bên mình. Okay. Good. Hello Keith. So thank for your presentation. So I think it's so late for you.
Yeah.
Yeah.
Well, thank you for everyone attending. Hopefully this was helpful. Feel free to reach out with more questions, and feel free to use this presentation as a starting point to develop a landslide risk assessment program. And we look forward to working more with you and answering any questions.
Yes. I will send the record and document to the customer. And if there any question from customer, I will collect and send it to you. Yeah.
Okay.
And thanks for your assistance. And goodbye. And
Okay.
good night. Yes.
Thank you.
Thank you.
Bye.
Goodbye.